Okay, welcome to Hottest. This is the last talk of the fall semester. The talks for next semester, at least the speakers for next semester, are posted on our website, so you can take a look at what's coming up. Today we have Matteo Spadetto from the University of Nantes, and he will tell us about different descriptions of the semantics of computation axioms. Please go ahead.
Thank you. Thank you, Dan. Thanks for this introduction and for the invitation. Today, I will give an overview of my research on different ways of describing, as you said, the semantics of type theory. And in fact, a big part of this work is based on a collaboration with Daniel Otten from the University of Amsterdam. Let's get started. So roughly speaking, this talk will be on how to express inference rules for dependent types, especially for the logical part of dependent types, in categorical structures. Hence, this talk will be about different ways in which we can in which we can define or characterize models of some of a given inference rule or of a given type former of Martin-Löf type theory, in order to ask ourselves whether a general structure is or is not a model of that given inference rule. Normally, or at least for this talk, in order to do this, we typically use the type theoretic language of a category. So if we have a category that has some notion of reindexing, this is achieved, for instance, when you have enough pullbacks, enough. So for instance, here I write, if C is a category with finite limits, then normally, according to this language, we regard its objects as context, and we regard at some, possibly all, arrows of codomain gamma as the encoding of our, and let's say as a semantic version of types A in context gamma. And once we stipulate that such an arrow corresponds to a type A, then we typically denote its domain this way, gamma.a, because we think of the domain as the context extension of gamma with a variable of type A. And then we regard at sections such an arrow as the semantic version of the terms of A in context gamma. For instance, this is the approach of Seeley in locally Cartesian closed categories and type theory. I will also briefly recall that if you are given in such a structure with pullbacks, a type A in context gamma and a substitution for gamma, then the interpretation, the validation of the reindexed type A in context delta, reindexed by F, will be represented by some pullback of this display map, we can call it a display map, via F. So normally you would need to have a choice of these pullback squares. Once you have a choice, then you define the interpretation of this type, assuming that this arrow already interprets a type A in context gamma, then the interpretation of this type will be this choice of a display map that constitutes a pullback square. And similarly, if you have a term T of type A, then the reindexed term judgment in context delta is represented by the unique section of the display map we have just talked about, such that the following diagram commutes. So using that this square is a pullback. If you have such a categorical structure where you can talk at least about reindexings of some arrows, then we can in fact use this internal type theory to formulate the type constructors of a theory, and hence, as I was saying before, ask ourselves if such a structure is or is not a model of a given type former of a given inference rule. So for this talk, I will distinguish between three approaches to formulate models. You may or may not agree with this distinction. Let's say that it is a distinction, between approaches that I use in order to explain myself during this talk. So first of all, I distinguish a syntactic approach where we typically encode these type formers, these type constructors into a structure, into such a general structure, because in fact these structures can be very general, can be of different types. In the syntactic approach, I was saying, we do the encoding of type constructors or of inference rules, let's say, into such a structure in alignment with the syntax. So we literally copy-paste the inference rules using the internal language we have just defined. Then there's another approach. I distinguish another approach, which is called categorical approach, or even higher categorical approach, where instead, in place of just reproducing the inference rules in such a structure, we prefer characterizing them via universal properties or via higher universal properties that are typically closure properties on the family of the arrows representing the types, for instance. So we use this other way to provide a more categorical characterization of type formers. And then I distinguish another approach, which you may regard as a part of the higher categorical approach. But for this talk, I wanted to maintain it distinguished, the homotopy theoretic approach, which is similar to the categorical approach in the sense that both these two approaches have in common that they do not explicitly refer to the syntax in principle. In both cases, we use categorical properties to hide the syntax. But I wanted to maintain this distinguished from this because in the homotopy theoretic approach, we rely more on a primitive notion of weak equivalence that is usually present in these structures, that normally these structures are equipped with. In this talk, I will talk about intentional type constructors, where you have definitional equalities, where you have term equality judgments as beta rules for your elimination principles, as J and split for identity types and dependent sum types. And I will talk about their axiomatic versions, where instead you just have terms in the corresponding identity types, which are called either propositional computation rules or computation axioms. There are several structures to phrase a model of a given type former, of a given inference rule. Some of which are, like the difference between these structures is that some of them are behave better with respect to the structural part of a dependent type theory. Others are don't behave like do not satisfy everything of the structural part of the type theory. For today, I will use the notion of a display map category to talk about these things, these semantic aspects of the inference rules of A-type theory. And the display map category is a category with a terminal object and with a distinguished family of arrows, which are called the display maps. And these are the arrows that we use to talk about type judgments, while the sections of these display maps correspond to terms of the types validated by these display maps. So as I was saying, we have the syntactic approach where we copy-paste type constructors into a display map category by means of choice functions in the language we defined before. So we will just replace every type judgment via a display map and every term judgment via a section of an appropriate display map. While, as we said, in the category theoretic approach, we look for one-dimensional categorical properties characterizing type constructors, allowing a choice function, as in the syntactic approach, to be automatically defined, to be automatically induced by this property. So in this sense, the categorical approach is a reformulation to the syntactic approach, is a reformulation of the notion of a model of an inference rule, in the sense that these properties that we look for, they should automatically induce choice functions, as in the syntactic approach, choice functions corresponding to the inference rules of type theory. And as we said, in the homotopy theoretic approach, the approach is similar, but the emphasis is more on the family of the weak equivalencies. While in the category theoretic approach, the properties are typically closure properties on the display maps. So just to clarify, let us talk about identity types. We are in a display map, and we want to see if that display map is a model of the formation rule of identity types. It is a model of the formation rule of identity types when, for every display map, PA, there is a choice of another display map in this context, which represents the context gamma extended with two variables of type A. So this is exactly the formation rule of identity types, which tells us if you have a type A, then you have a new type in the context of A extended with two variables of type A, which is exactly what we are saying here, but replacing the word type with the word display map. And similarly for the introduction rule tells us, look, if you give me a type A in context gamma, then I'll give you back a term of type x equals x, where x is a variable of type A. And this is exactly what we are asking here, a choice function that to every display map gives back a section of the display map interpreting that type, interpreting the type x equals x. And then, I'm not going to read this in detail, but the idea is similar for the elimination rule and the computation axiom. For every interpretation, for the interpretation of every instantiation of the premises of the elimination rule, a choice function will produce an interpretation of the conclusion of the elimination rule. And similarly for the computation axiom. So in the syntactic approach, you see many requests, many choice functions to have what we call a model of identity types, or at least a pre-model of identity types. I will talk about this later. While in the categorical approach, where we look for properties that characterize such choice functions, In the case when identity types are extensional, to have a model is just to have a display map where is just to have a display map category where for every display map, the corresponding diagonal arrow, which is the interpretation of the axiom rule, is isomorphic to another display map. So if you have a choice, actually, you also have a choice of this isomorphism, then you are able to recover such choice functions validating the inference rules. So it is a more compact, let's say, a more compact characterization of these choice functions. In the case when you have, when we are talking about extensional identity types, because when we want to talk about intensional or axiomatic identity types, things can be more complicated in the sense that maybe there aren't obvious one-dimensional categorical descriptions of the rules for intensional and axiomatic identity types. Just to make another example, dependent sum types. In the syntactic approach, to define a model, to say or to identify a model, you do as before, you rewrite the inference rules in a display map category by means of choice functions, while in the categorical approach, at least when we talk about extensional dependent sum types, there's a way more compact condition.
Looks like we lost him. Hopefully he'll come back in a moment.
Thank you.
Okay, we're back. Please continue.
Thank you. We were saying, yes, in the category theoretic approach, for extensional dependent sum types, we just have the condition that whenever you have two composable display maps, their composition is itself isomorphic to another display map. Again, this condition is enough to reobtain choice functions as in the syntactic approach. But again, when we consider intensional or axiomatic dependent sums, things can be more complicated. In the sense that, as I was saying, there aren't obvious categorical properties, one-dimensional categorical properties to talk about intensional and axiomatic identity types. So that is why we talk about the higher categorical approach, where we look for structures, higher dimensional categorical structures, in such a way that there is a bigger family, there is a wider family of properties for our display maps that we can require in such a way that we can characterize intentional type formers, rules for intentional type formers, without without making them collapse into their extensional version. What I mean is that once you add the dimensions, you can have more fine-grained properties to give to your display maps, to require for the display maps in your model, in such a way that you capture intensional identity types, intensional pi types, without making them extensional. So one of my lines of research is how to adapt this approach to axiomatic type constructors, and hence identify a higher dimensional structure with natural categorical conditions that allows to interpret axiomatic type forms. Now I'll say a few things regarding strictification issues of when we talk about models and pre-models of type theory. Seeley proved that as a display map category, finitely complete categories are almost models of extensional identity types and extensional dependence types. Because what I mean with almost, I mean that if you have a type A in context gamma and two substitutions, F and G, then the type A to which you substitute F and later you substitute G, and the type A to which you substitute F, to which you have already substituted G, will not necessarily coincide. And similarly, if T is a term of type A, so a section of a display map, then these two ways of performing the reindexing via substitutions F and G will not necessarily coincide. While, in this case, extensional Martin-Löf type theory always deduces these judgments whenever A is a type and T is a term of A. It means that a finitely complete category doesn't behave in a fully sound way with respect to some structural rule of dependent type theory. Hoffman studied this problem and proved that, in fact, every finitely complete category, which is in this sense a pre-model of extensional type theory, is equivalent to a split display map category, still endowed with extensional identities and extensional sigmas, where the word split means that there is a choice of pullback squares in such a way that this equality always holds. And also, I didn't write it here, but also the substitution behaves well with the type formers when you reindex type formers. This result was then generalized by Warren, showing that if you consider the inclusion of split display map categories into display map categories, this inclusion has a right adjoint whose co-unit is made of equivalencies, meaning that every display map category, once you apply this right adjoint, you obtain a split display map category, then you include it back to obtain a split display map category which is equivalent to the one that you started from. And additionally, under some pseudo-stability conditions, which are exactly the conditions that are satisfied by a finitely complete category, well, if these conditions you require them for a given display map category, then the right adjoint splitting will preserve extensional equalities and extensional sigmas. This was done by Warren, building on categorical result by Benabou and Streicher. This result, so this mapping from a display map category to a split display map category, well, let's say from a finitely complete category to a split display map category. So again, when I say split, I mean a genuine model. This mapping, I was saying, is proven to extend to a biequivalence between the two categories of finitely complete categories and an appropriate two category for whose objects are the contextual models of extensional identity types. This is a result by Clérambault and Dibier, and also Maietti studied this correspondence from another perspective. I also want to mention that this inclusion, when in the codomain you restrict to cloven display map categories, also has a left adjoint splitting. Which, again, okay, this time the unit of this adjunction is an equivalence, meaning that every cloven display map category will be mapped into a split one, equivalent to the given one, and under some weak stability conditions, again, this left adjoint preserves the semantic version of intentional identities and intentional sigmas. So this time we have a result for intentional identity types, and the conditions that need, the stability conditions that need to be verified in order to have this type theoretic structure to be preserved, to be maintained when you split a pre-model, is something weaker than the pseudo-stability, because in this case you only need that when you reindex the formation rule and the introduction rule of a given type former, like intentional identities, then in the domain of your substitution, you need to be able to find a new, in general, a new elimination rule that makes the reindexing of the introduction rule and the reindexing of the formation rule into a new type former of the same kind. But this new type former doesn't have to have anything in common with the type former of your choice, because I reminded that here we are talking about Cloven models, so we have a choice of intentional identity types. So this extension of the reindexing of formation and introduction doesn't have anything to do in particular with the choice of your type formers in the domain of a given substitution. This was done by Lansdale and Warren in the local universes model. So these two left and right adjoint splitting functors can be seen as coherence results for extensional identity types, for models of extensional identity types, and models of intentional identity types. In the sense that if we have a pre-model, a model that doesn't behave well with the substitution, a model of extensional or of intentional identity types, under some conditions, it admits a split replacement. Together with Daniel Otten and I, Daniel Otten and I asked if we could obtain a similar result for axiomatic identity types. So maybe this is a good occasion to briefly motivate the study of axiomatic type formers. Well, the idea is semantic. The idea is that a model of axiomatic type formers, where computation rules are weaker, are computation axioms, models of these type formers in principle need less equalities, less coincidences to happen to be satisfied. So in general, the axiomatic version of the intentional identity types would have more models than the ones of intentional identity types. So in principle, in general, it would be easier to produce models. You would have more models. In order to build a model starting from the mathematical nature, starting from the categorical nature, you would need to make less things to be satisfied. Then, this is not unrelated from the other reason that people believe, it is still a conjecture, there are some preliminary results, but there is a strong belief that axiomatic type theory, axiomatic Martin-Löf type theory is conservative. Sorry, that intentional Martin-Löf type theory is conservative over axiomatic type, Martin-Löf, over the axiomatic version. If this is true, then, since we are talking about different descriptions of semantics of type theory, if this is true, you could use the semantics of ATT to study ITT, to study intentional type theory. So the idea is not that we do this for the sake of axiomatic type theory, we do this because we want to use the semantics of axiomatic type theory to talk about intentional type theory. So the target is still intentional Martin-Löf type theory. So as I was saying, Daniel and I asked ourselves whether we could produce a coherence result for axiomatic identity types. And this time, we followed the homotopy theoretic approach to describe models. We used the notion of a path category, a notion which is similar to the notion of a model category. A path category, it was introduced by Benno van den Berg and Ike Moerdijk, exactly to have precisely to have a homotopy theoretic version of the semantics of identity types. It basically consists of a category with a terminal object, together with a class of vibrations and a class of weak equivalencies, in such a way that some properties are satisfied. Let us have a look to the axiom number 6 that tells us that whenever X is a context, an object of C, its diagonal factors as a weak equivalence followed by a vibration. Here, the idea is that the class of the vibrations will be our class of display maps. So our family of arrows that we use to talk about types, which is type theoretically, it may be regarded as a disadvantage, basically because vibrations are closed by composition, which means that you cannot distinguish between types in context and contexts in context. There's no distinction anymore between a type judgment in a given context and a sequence of types in a given context, because this depends on the fact that these display maps, these vibrations are closed by composition. However, it is an advantage in order to do some category theory in a path category. But for now, we look at this family of vibrations as our family of types, paying the price of not being able to distinguish between contexts in context and types in context in the internal type theory of a path category. So if we do this, if we follow this interpretation, then this vibration will constitute a type, will constitute a type in a given context. And the idea is that, similar to how it happens for model categories, this will constitute our identity types. This will constitute the formation part of our identity types, the validation of the formation rule. Now, as you may expect, if you like model categories, weak equivalencies and vibrations form a weak version of a weak factorization system. So weak equivalencies have a sort of a left lifting property with respect to vibrations and vice versa. What I mean with weaker? I mean that lower fillers will make the left lower triangle commute, but will not make the right upper triangle commute strictly. Okay, so maybe I should have painted this somewhere in a slide, but I didn't. Sorry about that, my fault. So I'll say it again, maybe. Suppose that you have a square with a commuting square with a weak equivalence on the left and a vibration on the right. In this case, you always have a filler for this square, as in weak factorization systems, but the left upper triangle will only commute up to a homotopy. A homotopy is a thing that you can always define in a path category, out of the weak equivalencies and these path objects. You can define it. It will be an equivalence relation between parallel arrows. And as I was saying, in a square with a weak equivalence on the left and a fibration on the right, there will be lower fillers that make the lower triangle commute, but the upper one only commute up to such a homotopy between parallel arrows. This is precisely the reason why these fibrations validate axiomatic identity types, but not necessarily intentional identity types. In fact, what happens is that homotopies between parallel arrows can always be rephrased as sections of appropriate path objects. But we said that path objects are identity types. So it means that homotopies are essentially sections of identity types. So they will be identity proofs. And that's why you obtain an identity proof, a computation axiom for the induction principle of identity types, but not a beta rule. So that is why, so this is a sort of intuition of the proof of the following result, that path categories are free models of axiomatic identity types, in the sense that they are contextual display map categories with axiomatic identity types. And they still have some extensionality principles. They have extensional unit types and extensional dependent sum types. This basically depends on point 1 for sigmas, for extensional sigmas, and point 5 for extensional units. So you still have some extensionality, and the reason is either problem or feature, it depends, that we regard types as fibrations, and that we lose distinction between context in context and types in context. When you lose this distinction, you always have extensional units and extensional sigmas. We asked ourselves if we could avoid this, and Daniel came up with a clever notion of a display map path category, where we have fibrations, weak equivalencies, and display maps. So display maps remain distinguished from fibrations in such a way that we can use display maps to talk about types and fibrations to talk something else, maintaining the distinction between types and contexts in the semantics, in the internal language in the internal type theory of a path category. In that way, as I was saying, you drop these extensional types, one types and sigma types, and then you can ask whether you can equip such when you can equip such a display map path category with extensional axiomatic versions of these type formers. I will not talk about this notion. So if you want to know more about this, you may invite Daniel for another season if you want to hear more about the display map path categories. For today, I just finished with the path categories. So now I'll still have 15 minutes to say something more about this. I was saying path categories are contextual display map categories with extensional unit types and extensional sigma types and axiomatic identity types, and vice versa. If you have a display map category with such a structure, then it is equipped with the structure of a path category. So we see some correspondence between a homotopy theoretic formulation and a syntactic formulation. Now, this result extends to a result similar to the one by Clérambault and Dibier. I will give the rough statement. There exists a biequivalence between the two category. Maybe I should precise, I should make the more precise. I will say in a bit what I mean. There exists a biequivalence between let's say an appropriate two category of contextual models of axiomatic identity types and other things, and the two-dimensional category of path categories, in the manner of the biequivalence between the two category of contextual models of extension identity types and the two category of finitely complete categories, which was obtained in a cumulative work that started from Seeley, passed through Hoffman and Warren, and finished with this result by Clérambault and Dibier. And I also name again the result by Maietti, which is a result like this from another point of view. Okay, so now I will try to give the more precise statement. So as you see here, I have some gaps to be filled. Here, for the one cells, for the morphisms between finitely complete categories and path categories, we put the functors that preserve the structure. However, so the so-called exact functors, which mean two different things. So exact functors are the ones that, for instance, for finitely complete categories, they are the ones that preserve limits. So for instance, for identity types, for equalizers, they send every equalizer to another equalizer in the codomain. For path categories, an exact functor is similar in the sense that it preserves, in this case, the structure of weak equivalences and fibrations. So it will send weak equivalences to weak equivalences, fibrations to fibrations, the terminal object to the terminal object, and the pullbacks of fibrations to pullbacks. Now, the point is that and you can also observe that with this notion of morphisms between path categories, if you restrict to finitely complete categories, because I should say that finitely complete categories are precisely those path categories whose weak equivalences are just the isomorphisms and whose fibrations are any map. In this case, you obtain the finitely complete, precisely the finitely complete categories. And if you restrict this notion of a one cell to the finitely complete categories, you do obtain the exact functors for finitely complete categories. So in some sense, this category extends this one. Now, the point is that in the moving to the syntactic formulation, so to this category and to this category, structure preserving functors means two different things. This is because universal data are pseudo-unique, as we know. Two equalizers of the same thing are isomorphic via a unique isomorphism. While homotopy, universal data, like path objects, are only weakly equivalent, weakly unique. They are unique only up to homotopy equivalences, and not unique homotopy equivalences, but homotopy equivalences that are unique up to parallel homotopy. So they are weakly unique. This is the reason why here you have data pseudo-preserving morphisms, and here you have data weakly preserving morphisms. Okay, now, in principle, as we know, as we said during this talk, finitely complete categories and path categories are three models that we need to strictify. Finitely complete categories, we are lucky because they induce pseudo-stable data that can be preserved by the right adjoint splitting. While path categories induce weakly stable data, and weakly stable data are only preserved by the left adjoint splitting. But we said before that using the left adjoint splitting, if we use the left adjoint splitting, we need pre-models in input to be cloven. We need them to have a choice of substitutions. And additionally, because of the results by Lambsdale and Warren, you need them to satisfy the logical framework condition. In other words, you need the internal type theory to have additional structural rules that tell us that you can build function variable contexts, that you can build contexts whose variables are function variables. It's a sort of it's like having extensional pi types, but that they are not types, that they are just pi contexts. So these function variables are not really typed by pi types. They are just a structural part of the type theory. They're just additional contexts, not additional types, additional contexts that we allow our internal type theory to have. This is called the LF condition. So in the end, the final statement is the following, that the domain category of this equivalence needs to be made of LF cloven path categories satisfying the logical framework condition. And in this case, this category will be equivalent to the category of the genuine models. So in the process of applying this equivalence, we strictify our cloven path categories, precisely as it happens in the result by Clérambault and the DPA. With the only difference that here we have hidden the right adjoint splitting, while here we have hidden the left adjoint splitting. So in particular, this was the motivation to start this. The motivation to start this was to have a coherence result for models of axiomatic identity types. This is achieved thanks to this by equivalence, that some path categories, namely the LF cloven path categories, are equivalent to split path categories, so they have a split replacement, because basically you have to start from an LF cloven path category here. You strictify it using the equivalence, and then by using the result of before, since this will be I forgot to write contextual in front of model here and here. So since it will be a contextual split display map category with these type formers, because of the result of before, it will itself be endowed with a structure of a path category, which will be split. So we obtain such a coherence result that LF cloven path categories are equivalent to strict path categories. We have such a coherence result, which is phrased in the homotopy theoretic formulation of the models of axiomatic identity types. As I said, there is a notion by Daniel, which also drops the extensional type formers in a path category. And this will be the last thing that I say in the last 5 minutes, that all of these also has a categorical counterpart. So now we talked about the homotopy theoretic approach for the semantics, in this case of axiomatic identity types. And now I would like to briefly move back to the higher categorical formulation of axiomatic type formers, axiomatic identity types. I want to briefly explain that there are also higher category theoretic data rather than homotopy theoretic data to talk about axiomatic type theory in a model. As you may imagine, as in model categories, in every path category, a higher dimensional category is hidden. This was studied by Martijn den Besten. The idea, as in model categories, is that if you have two parallel substitutions, two parallel one-dimensional, two parallel arrows in a path category, then we can stipulate that a true cell between them is a homotopy. Homotopies, as I said before, can also be seen as sections of appropriate path objects. They can be, okay, let's say they are defined in some way, and we use them as our notion of true cell between parallel morphisms. Now, since they also are themselves, since these homotopies are themselves one cells, because you can see them as sections of path objects, you can go on. So you can also consider homotopies between parallel homotopies. Anyways, for today, for the sake of simplicity, for these last 5 minutes, let us just stop to dimension 2, which means we have to quotient the two-dimensional level. In place of considering homotopies between parallel one cells, we consider as two cells, we consider equivalence classes of parallel homotopies, where the equivalence relation is itself a homotopy. So two parallel homotopies will live in the same equivalence class if they are themselves homotopic. In this way, den Besten proved that path categories are in fact enriched in groupoids. And the thing that you can observe is that fibrations are cloven isofibrations, in the sense that whenever P is a fibration and you have a triangle that commutes up to homotopy, then you can find a new arrow which is parallel to G, which makes the lower triangle commute, up to lifting this two-dimensional cell to a new two-dimensional cell between these two parallel arrows. A second condition that you can observe is that path objects are in fact homotopy arrow objects. Whenever you have a two-dimensional cell from delta into gamma prime, so yeah, here I am considering the category of the arrows in this slice category, which means the objects are two-dimensional cells into gamma prime. Each one of them factors through a one-dimensional cell into a path object. And this factorization forms an equivalence of categories, which is naturally in delta. This basically follows from our characterization of homotopies as sections of path objects. And finally, another categorical condition that you can obtain is that pullbacks are also two-dimensional pullbacks. What I want to focus on is the first thing, the fact that fibrations are cloven isofibrations. In particular, they are not necessarily normal isofibrations, which means that if you lift the identity to cell, you will not necessarily obtain the identity to cell. And this can be seen if we remember that path categories in general only have axiomatic identity types, not necessarily intensional identity types. Okay, since I'm running out of time, I will keep these for later if one is interested in knowing the syntactic reason why fibrations in a path category are cloven isofibrations, but not necessarily normal isofibrations. This is very important If one is interested, I can explain later the syntactic reason behind this. I will just conclude by saying that, okay, from path categories, homotopy theoretic models, we can extract these purely higher category theoretic data. Now, if you have a display map to category, so we go back to the higher categorical framework, the higher categorical formulation. If you have a display map category where you also have two-dimensional cells between one cells, then you can require precisely these categorical conditions that are, in principle, now they are not homotopy theoretic. They do not talk about weak equivalencies anymore. Well, it happens that these category theoretic data are enough into, if you require them into such a structure, so if you require these conditions, they are enough to rebuild the semantics of axiomatic identity types as in the syntactic approach, and without necessarily validating the judgmental computation rule for intensional identity types. So they will be models of axiomatic identity types, once you translate them as in the syntactic approach, that do not necessarily happen to be models of intensional identity types. So I wanted to briefly comment how from the purely homotopy theoretic approach, we are able to re-obtain purely category theoretic aspects that allow us to recharacterize the syntax of, in this case, of axiomatic identity types, but also for higher type formers, also for other axiomatic type formers. But for now, I just wanted to say this for axiomatic identity types. Okay, I will stop here and thank you for listening to this talk.
Great. Thank you very much, Matteo. We will do our silent or emoji applause.
Thank you. Thank you.
Okay, I'll open the floor to questions. Please just unmute your mic if you have a question. Okay, I see a couple of people have their hands up, so I don't know the order. Oh no, sorry, that was the applause. Okay, so if anyone wants to ask a question, please unmute and go ahead.
Hello?
Yes.
Hello.
Hi. Yeah, hi, Matteo. It's Josh. Yeah, thanks for the nice talk. I was a little bit confused. Maybe it's just a confusion on my part, but I think every path category is a model of, well, every path category models propositional identity types, which, if I understand correctly, are your axiomatic identity types. Is that correct?
Yes.
Yeah.
Yes.
So I was just wondering, yeah, because I think on your slide, I was a bit confused when you said, what was it? There was a slide titled Non-Genuine Models of Axiomatic Identity Types, and where you had the definition of path category.
True.
So I was
Let me
just,
go back to that.
I was just wondering, when I saw that title, I was like, I didn't quite understand that. So is that a typo, or is that
No,
addressed by what
it's
you said after?
thank you for this question, Josh.
Hmm, hmm,
It's just what I meant is
hmm.
that path categories, in principle, yeah, they are models of axiomatic identity types, but in principle, they are not well as in this definition, they do not even have a choice of substitutions. So far, you cannot even talk about substitutions. But even when you have a choice of substitutions, you have the similar problem of finitely complete categories, that the substitution may not be functorial, that it doesn't behave well with path
Also, you're
objects.
referring to that aspect of the type theory.
Exactly. So they are
Okay.
pre-models of this type theory.
Mm,
They do not
I see.
necessarily behave well with the structural rules. That is why I said non-genuine. I should have said pre-models, maybe.
I understand. Okay, thanks.
Thank you.
Okay, someone else have a question? I actually have a question about this slide, so maybe I'll jump in. Can you say what's different between path categories and vibration categories?
I think that in place of I think the main difference is that in place of 2 out of 3, you have a 2 out of 6.
Okay.
So it's a stronger condition. If you have 3 weak equivalencies, composable weak equivalencies, then in such a situation you have 6 arrows. These 3 arrows, or the composition of any 2 of them, or the composition of the whole of them. This identifies 6 arrows, and when 2 of them are weak equivalencies, then all of them are weak equivalencies.
Okay. Okay, I didn't notice that subtlety because everything else looked about the same as far as I could remember. Thank you.
But I think there's, thank you for the question then. I think there's another detail more that a path category has more. But so far I cannot, in this moment, I cannot tell which it is, but there was another thing, another subtle difference.
Yeah.
Maybe
Could it
if Daniel is here in the audience, I don't know if he is in the audience, then he knows for sure. Okay.
Okay. Are there more questions?
But were you saying something then? Were you trying to guess what it was?
Well, I did have one thing that I wasn't sure if it's part of a vibration category. In item 5, every trivial vibration has a section. I
Oh,
can't
right.
remember.
It was that one.
Oh,
It was
okay.
that one, exactly.
Okay, good.
Thank you.
Okay. Any more questions? All right. Well, I guess we will thank Matteo again. And as I mentioned at the start, this is the last talk of the semester. We'll start up again in February, and the speakers and dates are on our website. See you then.